I would like to start by apologizing for any potential noise, and I hope it won't be too disruptive. I will display each cell of the Excel to identify the equations. Let's present in this lecture the calculation for the hybrid rocket engine design. The fuel used will be the paraffin, and the oxidizer is the nitrous oxide, the N2O. The engine provides 1.5 kN of thrust with a chamber pressure of 30 bar and the oxidizer to fuel ratio or the OF ratio of 5. For the calculation of C star, the equation 1 here is used with these coefficients and with an efficiency of 80%, resulting in a C star of 1263 meters per second. Other initial design parameters are include the thrust coefficient, the CF, the expansion ratio, and the specific inputs are presented here. The oxidizer and fuel data are as follows. The tank pressure is about 55 bar. The initial port diameter is 0.03 with time step of 0.1 seconds and a burning time of 5 seconds. Now, using the equation 2, we can find the thrust area. Using the equation 3, we determine the thrust diameter. Using the expansion ratio, we obtain the nozzle XD area. Similarly, we find the exit diameter as we did for the thrust. The terms height corresponds to the square root of the number inside the parentheses. And to find the length of the nozzle, assuming the optimal expansion angle is 12 degrees, this angle here, we use the equation 5 and algebra to calculate the length. From here, let m dot be the mass flow rate of the propellant, or oxidizer, or fuel. To calculate the m dot of the propellant, the equation 6, the characteristic velocity equation, is used. And now considering the equation 7, knowing that m dot of oxidizer plus the m dot of fuel equals m dot of the propellant, we obtain the equation 8 in terms of the OF ratio to calculate the m dot of fuel. Here. Then we reuse the equation 7 to find the m dot of the oxidizer. Finally, the mass of the oxidizer and fuel is the m dot times the burning time, given by the equation 9. The total mass will be the mass of the oxidizer plus the mass of the fuel. Now we can define the number of the injector orifice. I define it as 5. And to find the area of each orifice, we use the Bernoulli equation divided by 5, as in the equation 10. And for the orifice diameter, we use again the equation 3, the same for the thrust and the exit diameter. For the oxidizer tank calculation, knowing that density is the mass divided by the volume, we use the equation 11 to find this total volume. The tank diameter is chosen by me, set as 0.09 meters, with the tank volume and the base area. For a cylindrical tank, we find the tank length using the equation 12 here. And the thickness is based on equation 13, where SF is the surface factor, defined by me as 2. PB is the burst pressure, and the burst pressure is the 2 times the tank pressure. The RC is the radius tank radius, and the FTU is the ultimate tensile strength. We chose aluminium with 414 megapascal. This is the equation. In addition, to find data for the fuel, we must use an iterative method with the initially defined time step as 0.1 second. The regression rate, here the R dot, is given by the equation 15, where A and N are experimental coefficient. I put they here. And G is calculated by equation 14. Divided by the port area, the initial port area, and using the equation 15 we can calculate the R dot. We divided 4,000 because here is millimeters and we need in meters. We input the initial radius and the radius at the next time step, n plus 1. We calculate the port area again and repeat the calculation with a constant oxidizer mass flow rate. At the end of this process, we find the final radius at the burning time. Wait, this column. We have the radius of the fuel, so we have the time by 2, the double of this number, and you find the diameter of fuel. And the grain length is also calculated considering the cylindrical grain, but with the fuel ring. Here is the equation. Here are other parameters such as the OF ratio, the characteristic velocity, the chamber pressure, and the generated forces, and the initial m dot of fuel. I will display the cells to illustrate how the calculation is done for these parameters. For the OF, this is the same equation for the first characteristic velocity. Chamber pressure, we divided by 10 power 5 to find in bar, not in Pascal, and the generated forces. The design of this engine is represented in the following figure. And for the innovation, I would propose the addition of the small thermoelectric generator to recover thermal losses and generate electricity to power spacecraft electronics. Another proposal is the optimization of the burning profile, such as a variable thrust profile for different flight phases. And however, these require the creation of a ring system that can change the nozzle length to take advantage of the efficiency curve.